Welcome to Atomic Domain, the channel where the mysteries of space and time unfold. Today, we embark on a journey through one of the most fascinating and enigmatic phenomena in the universe, black holes. These objects, often depicted in movies as cosmic vacuums swallowing everything in their path, are much more than just science fiction. They are real, they exist, and they hold secrets that could change everything we know about the universe. But what exactly is a black hole, and how do they form? Imagine a place in space where gravity is so intense that nothing, not even light, can escape its pull. This is the fundamental nature of a black hole. What makes them even more intriguing is that they are invisible. Black holes do not emit light, making them nearly impossible to detect directly. Despite their invisibility, scientists have devised clever methods to study these cosmic giants. But to truly understand them, we first need to explore their formation, their properties, and the way they bend the very fabric of space and time. In this video, we will unravel the mechanics of black holes, from their formation after the death of massive stars to their role in shaping galaxies. We will explore how black holes warp spacetime and how researchers detect them through indirect methods such as gravitational waves and X-ray emissions. So, buckle up as we embark on this cosmic adventure and unlock the secrets of black holes. At its core, a black hole is defined by its immense gravitational pull, a force so strong that it warps space and time in such a way that nothing, not even light, can escape from it. The point at which nothing can escape is known as the event horizon. To understand this concept, we need to explore the idea of spacetime, the fabric that makes up the universe, according to Einstein's theory of general relativity. Spacetime is a four-dimensional continuum that combines the three dimensions of space with time. Objects with mass, like stars and planets, cause spacetime to bend. This bending is what we perceive as gravity. A black hole takes this bending to an extreme degree. As mass collapses inward, it warps spacetime so drastically that a boundary is created around the black hole known as the event horizon. Once something crosses this boundary, there is no escape. Even if you were traveling at the speed of light, it would be impossible to escape the event horizon. An important thing to note is that the event horizon does not mark the edge of the black hole in the traditional sense. Rather, it's a point of no return. Inside the event horizon, all paths lead to the singularity, the heart of the black hole, where gravity becomes infinite. The concept of an event horizon is one of the key features that makes black holes such mysterious objects. It's the point at which our understanding of the universe begins to break down, and physics, as we know it, no longer holds up. But while black holes themselves remain invisible, scientists have developed clever methods to detect their presence. The most notable of these is through the effects they have on surrounding matter. As matter gets pulled into a black hole, it can accelerate and heat up, emitting high-energy radiation that we can detect using telescopes. This process allows us to identify regions in space where black holes are lurking, and by studying their influence on nearby stars and gas, scientists can infer the properties of these. To understand how black holes come into existence, we need to explore the life cycle of a massive star. All stars, including our Sun, are powered by nuclear fusion, a process that fuses lighter elements into heavier ones, releasing enormous amounts of energy in the process. This energy counters the force of gravity, keeping the star stable and preventing it from collapsing in on itself. However, a star with a mass several times that of the Sun will eventually exhaust its nuclear fuel. When this happens, the balance between gravity and fusion energy begins to shift. The star's core starts to collapse under its own gravity, while the outer layers may explode in a supernova, a powerful explosion that can outshine an entire galaxy for a brief period. What remains after the supernova explosion is crucial to whether or not a black hole forms. If the remaining core is massive enough, typically more than 3 times the mass of our Sun, the force of gravity overwhelms all other forces, and the core collapses into a point of infinite density known as the singularity. This marks the birth of a black hole. The process of stellar collapse is governed by the equation of state of the core material, meaning how the particles behave under extreme conditions. As the core becomes denser, it can no longer support itself through normal processes of electron degeneracy pressure, which supports white dwarfs, or neutron degeneracy pressure, which supports neutron stars. When this happens, the star's core collapses to form a black hole. Interestingly, the size of the resulting black hole is not directly tied to the size of the star. A black hole can be incredibly small, with a mass several times that of the Sun compressed into a tiny point. This is known as the Schwarzschild radius, and it is the key to understanding the incredibly dense nature of black holes. Once formed, a black hole begins its influence on the surrounding space, bending and distorting spacetime in ways that we are only beginning to fully comprehend. The incredible power of black holes stems from the way they warp spacetime, a phenomenon predicted by Einstein's theory of general relativity. According to this theory, gravity is not just a force pulling objects together. It's a result of the curvature of spacetime caused by mass and energy. Essentially, massive objects like stars, planets, and black holes bend the fabric of spacetime around them, and this bending is what we experience as gravity. To visualize this, imagine spacetime as a stretched rubber sheet. If you place a heavy ball on the sheet, it will create a deep indentation, bending the fabric of spacetime. Now, if you roll a smaller ball across the sheet, it will curve toward the indentation, mimicking how objects move in the gravitational field of a planet or star. In the case of black holes, the gravitational field is so strong that the fabric of spacetime is warped to such an extreme degree that it forms a well so deep that nothing can escape. This warping is more than just a distortion of space, it also affects time. The closer you get to a black hole, the more time slows down relative to an observer farther away. This effect, known as time dilation, is another key prediction of general relativity. If you were to fall toward a black hole, time would seem to slow down as you approached the event horizon from the perspective of an outside observer. At the event horizon, time essentially stops relative to the outside universe. This is one of the most mind-boggling aspects of black holes. Once something crosses the event horizon, time and space become indistinguishable, and the normal laws of physics break down. Within this extreme environment, scientists struggle to apply the known laws of physics, which is why the study of black holes often leads to more questions than answers. In the world of black holes, the event horizon is the ultimate boundary. It is the point beyond which no object or information can escape, not even light. The event horizon represents the threshold at which the warping of spacetime becomes so extreme that all paths lead to the singularity, a point of infinite density at the black hole's center. To truly understand the significance of the event horizon, we need to look at the nature of the singularity itself. At this point, the gravitational force becomes infinite, and the curvature of spacetime is so extreme that the known laws of physics no longer apply. The singularity is, in essence, a point where all the mass of the black hole is concentrated into an infinitely small volume. But what happens when something crosses the event horizon? If an astronaut were to fall into a black hole, from their perspective, time would continue as normal, but from an outside observer's point of view, the astronaut would appear to freeze at the event horizon. This phenomenon is due to the extreme time dilation caused by the black hole's gravity. As for what happens inside the event horizon, we can only speculate. It is believed that once inside, matter is inevitably pulled toward the singularity, where the gravitational forces become so intense that the matter is crushed into a singularity. This concept challenges our understanding of space, time, and the fundamental laws of physics. The singularity and event horizon are also at the center of a major mystery in modern physics, the search for a theory of quantum gravity. Current theories of physics, such as general relativity and quantum mechanics, break down when applied to the extreme conditions near a black hole's singularity. Resolving this paradox is one of the greatest challenges in physics today. Black holes come in several types, each distinguished by their mass, size, and the way they affect their surroundings. The three primary categories of black holes are stellar, supermassive, and intermediate black holes, each of which has distinct properties and plays a unique role in the universe. Stellar black holes are the most common and are formed when massive stars, typically with a mass of at least 20 times that of the Sun, run out of fuel and undergo a supernova explosion. What remains after the explosion is the core of the star, which collapses into a singularity. Stellar black holes generally have masses between 3 and 10 times the mass of our Sun. These black holes are found scattered throughout the universe, particularly in regions with high star formation activity. Despite their relatively smaller mass compared to supermassive black holes, stellar black holes are still incredibly powerful. They can affect nearby stars and gas clouds, bending light and distorting space-time. Because stellar black holes often reside in binary systems, they can be detected by the X-rays emitted when they pull in matter from a companion star. As the material spirals into the black hole, it heats up and releases radiation, which astronomers can observe. At the centers of most galaxies, including our own Milky Way, lies a supermassive black hole. These black holes have masses ranging from millions to billions of times that of the Sun. While the exact mechanisms behind their formation remain a mystery, it is believed that supermassive black holes either grew from smaller black holes over billions of years or formed early in the universe through the collapse of large gas clouds. Supermassive black holes play a key role in the dynamics of galaxies. Their gravitational influence can affect the orbits of stars and gas clouds, helping to shape the overall structure of galaxies. In some cases, supermassive black holes are surrounded by accretion disks, which are rotating disks of gas and dust. The material in these disks is heated to extreme temperatures as it spirals toward the black hole, emitting radiation across a wide spectrum, including X-rays and gamma rays. These emissions allow astronomers to study the properties of supermassive black holes. Intermediate black holes occupy a size range between stellar and supermassive black holes, with masses ranging from 100 to 1,000 times the mass of the Sun. They are more difficult to detect as they do not emit the intense radiation seen from stellar or supermassive black holes. However, recent observations suggest that intermediate black holes may be more common than previously thought. One way that intermediate black holes are thought to form is through the merger of smaller stellar black holes. This process could create a black hole with an intermediate mass. Alternatively, some scientists believe that these black holes could form from the collapse of massive clusters of stars, resulting in a concentration of mass that eventually collapses into a black hole. In addition to these three main types, there is also the theoretical possibility of micro-black holes, which would have extremely small masses. These black holes could have been formed during the early universe as a result of high-density fluctuations in the fabric of space-time. If they exist, they would be incredibly difficult to detect because they would emit very little radiation. Micro-black holes are purely theoretical at this point, and no evidence has yet been found to confirm their existence. One of the most exciting advancements in modern astrophysics has been the detection of gravitational waves, ripples in spacetime caused by the acceleration of massive objects like merging black holes. These waves, predicted by Einstein's theory of general relativity, provide us with a new way of studying black holes and their interactions. Gravitational waves are disturbances in the curvature of spacetime that travel outward from their source at the speed of light. They are produced whenever massive objects such as black holes or neutron stars accelerate and cause ripples in spacetime. When these waves reach Earth, they can be detected using extremely sensitive instruments such as the Laser Interferometer Gravitational Wave Observatory LIGO and Virgo. In 2015, scientists working with LIGO made the groundbreaking detection of gravitational waves from the merger of two stellar mass black holes. This marked the first direct observation of black holes colliding and merging, providing strong evidence that black holes are not just theoretical objects but real phenomena that shape the universe. This discovery opened up a whole new field of astronomy known as gravitational wave astronomy. The detection of gravitational waves from black hole mergers has allowed scientists to study black holes in ways that were previously impossible. When the black holes spiral toward each other and merge, they release an enormous amount of energy in the form of gravitational waves. These waves carry information about the masses, spins, and other properties of the black holes involved in the merger. By analyzing the frequency, amplitude, and other characteristics of the gravitational waves, scientists can learn about the properties of the black holes that produced them. For example, the first detection of gravitational waves revealed that the two black holes involved in the merger had masses of about 29 and 36 times the mass of the Sun. The merger produced a black hole with a mass of about 60 to solar masses. Gravitational wave astronomy is still in its infancy, but it has already provided us with valuable insights into the universe. In addition to helping us study black hole mergers, gravitational waves can also be used to observe other violent cosmic events, such as the collisions of neutron stars, which can lead to the formation of black holes. Gravitational waves also offer a unique opportunity to test Einstein's theory of general relativity in extreme environments. By studying the behavior of gravitational waves near black holes, scientists hope to gain a deeper understanding of the nature of spacetime itself and possibly uncover new physics that could explain phenomena such as the singularity. One of the most bizarre and fascinating effects near black holes is the phenomenon known as spaghettification. This term refers to the extreme stretching and elongation of objects as they fall into a black hole due to the tremendous difference in gravitational forces acting on them. It's a dramatic visual that highlights the unique and extreme nature of black holes. Spaghettification occurs because of the intense tidal forces near a black hole. As an object moves closer to the event horizon, the gravitational pull on the part of the object that is closest to the black hole becomes much stronger than the pull on the farthest part. This difference in gravitational forces causes the object to be stretched along the direction toward the black hole, turning it into a long, thin shape, like a piece of spaghetti. For example, if a human were to fall feet first into a black hole, the gravitational pull on their feet would be far greater than the pull on their head. As a result, the person would be stretched and elongated as they fell deeper into the black hole. This process continues until the object is ultimately stretched into a thin, elongated strand of matter. Spaghettification is a direct consequence of the intensity of the gravitational field near a black hole. The closer an object gets to the event horizon, the stronger the tidal forces become. For smaller objects like asteroids or spacecraft, the effects of spaghettification are not immediately noticeable, but for larger objects, such as a human or a star, the stretching effect becomes fatal. Once the object reaches the event horizon, all the forces acting on it are directed toward the singularity at the center of the black hole. The object's matter is ultimately crushed to an infinite density at the singularity, and it disappears from our observable universe. The spaghettification process highlights just how extreme the forces of nature are near black holes, and serves as a reminder of how little we truly understand about the inner workings of these cosmic giants. Although black holes are often thought of as destructive, they also play an important role in the evolution of the universe. These cosmic giants are not just destroyers, they are also cosmic recyclers. Black holes, particularly supermassive black holes, have a profound impact on the formation and behavior of galaxies, stars, and even the fabric of spacetime itself. At the center of most galaxies, including our own Milky Way, resides a supermassive black hole. These black holes have masses that are millions or even billions of times that of the Sun, and they exert immense gravitational influence over the surrounding galaxy. The presence of a supermassive black hole can regulate the movement of stars and gas within the galaxy, affecting everything from star formation rates to the overall shape of the galaxy. The influence of supermassive black holes on galaxy formation is still an area of active research, but it's believed that these black holes play a key role in galactic evolution. For example, as matter falls into a black hole, it can be expelled in the form of high-energy jets that can push out surrounding gas and prevent new stars from forming. This process helps regulate the size and growth of galaxies and may even determine their ultimate fate. In addition to their role in regulating galactic growth, black holes can also act as engines for star formation. When gas and dust are pulled toward a black hole, they can form accretion disks that spin at incredibly high speeds. These disks can become so hot that they emit radiation across the electromagnetic spectrum, including visible light, X-rays, and gamma rays. In some cases, the energy released by these accretion disks can trigger the formation of new stars in the surrounding gas clouds, creating a cycle of cosmic regeneration. The complex relationship between black holes, galaxies, and star formation is a topic of great interest to astronomers. By studying the influence of black holes on their host galaxies, scientists can learn more about it. The study of black holes has come a long way since their theoretical prediction over a century ago. From the first direct imaging of a black hole's event horizon to the detection of gravitational waves, black hole research is now one of the most exciting frontiers in astrophysics. Yet, despite all the progress made, there are still countless mysteries surrounding these enigmatic cosmic objects. In this final part, we'll explore the future of black hole research, the questions that remain unanswered, and what the future holds for our understanding of the universe.
In April 2019, the Event Horizon Telescope EHT made history by capturing the first-ever image of a black hole's event horizon. This groundbreaking image, showing the shadow of a supermassive black hole in the center of the galaxy M87, was a monumental achievement. The EHT used a network of radio telescopes round the world to create a virtual Earth-sized telescope capable of observing the black hole at unprecedented resolution. However, this image only represents the first step in a long journey. The image revealed the shadow of the black hole, but there is still much to learn about its internal structure and the surrounding environment. Future observations with more advanced technologies, like the next-generation EHT, will continue to refine our understanding of black holes and may even offer a glimpse into the event horizon itself. One of the biggest unsolved mysteries in black hole research is the information paradox. According to the principles of quantum mechanics, information about a physical system should never be lost. However, when matter falls into a black hole, it seems to disappear from the observable universe, leading to the paradox. Where does the information go? This puzzle has perplexed scientists for decades, and despite some progress, there is still no consensus on the solution. Some theories suggest that information is somehow preserved on the event horizon, while others propose that it could be encoded in the radiation emitted by black holes through a process known as Hawking-G radiation. Resolving the information paradox could be key to reconciling quantum mechanics with general relativity, two of the most fundamental theories in physics. Another exciting area of research involves simulating black holes in the laboratory. Although it is impossible to create a real black hole on Earth, scientists have been developing analogs that can mimic some of the properties of black holes. For example, researchers have used lasers and other materials to create event horizon analogs in fluid dynamics experiments. By studying these artificial black holes, scientists hope to gain insights into the behavior of real black holes and the mysterious phenomena that surround them. While stellar and supermassive black holes are well studied, there is still much to learn about black holes of intermediate size, as well as the potential existence of primordial black holes. Intermediate black holes, with masses between stellar and supermassive black holes, are difficult to detect, but their existence has been strongly suggested by observations of gravitational waves and unusual stellar behavior. Understanding these intermediate black holes could provide important clues about the formation of black holes in the early universe.
Primordial black holes, which are theorized to have formed shortly after the Big Bang, could provide a window into the conditions of the early universe. If they exist, they might account for some of the dark matter in the universe, although no evidence has yet been found. Research in these areas will be crucial for understanding the full spectrum of black holes and their role in the cosmos. In the distant future, black holes may even play a role in the ultimate fate of the universe. One theory, known as the Big Rip, suggests that the universe will continue to expand at an ever-accelerating rate, eventually tearing apart galaxies, stars, and even atoms. In such a scenario, black holes could become the last remaining objects in the universe, slowly evaporating over unimaginable time scales through the process of Hawking radiation. This idea leads to a profound question. If all black holes eventually evaporate, what happens to the information they've consumed? While the ultimate fate of black holes and the universe remains unclear, ongoing research and technological advancements continue to push the boundaries of our knowledge. As scientists delve deeper into the mysteries of black holes, we may soon unlock even greater secrets about the nature of space, time, and the cosmos itself. The mechanics of black holes are among the most fascinating and mysterious topics in modern science. From their formation to their role in shaping galaxies, black holes have a profound impact on the universe. Thanks to advancements in technology and groundbreaking discoveries, our understanding of these enigmatic objects has grown exponentially. Yet, despite all we've learned, black holes still hold many secrets, and the journey to unlock those secrets is far from over. As we continue to explore the wonders of the cosmos, we invite you to join us here at Atomic Domain as we dive deeper into the mysteries of space, science, and technology. If you enjoyed this video and want to stay up to date with the latest discoveries, don't forget to like, comment, and subscribe. Share your thoughts in the comments below, and let's continue exploring the universe together.